MATH555 series solutions near a regular singular point. Suppose we have an equation given in this form, and if we have two conditions, p of x naught is 0, and the limit of q over p times x minus x naught, x goes to x naught, equals a, limit x r over p x minus x naught squared converges to b, then we can say it's a regular singular point, and we can write down the limit equation. And from now on, we will assume x naught equals 0. Okay, just for simplicity. Then the limit equation will be just written in the Euler equation form: x squared double or y double prime plus ax y prime plus by equals 0. Then we claim that this equation will give you two solutions: y equals xr1 and y equals xr2. Right? Then we will do this xr1 xan xn when equals 0 to infinity. So our new solution, the solution for the original equation, will have also two solutions. One is very similar to x to the r1, and the other is very close to x to the r2. And this a and that a are two independent theories. They may be different. So if this approximately is just a0, right? So you can say when x is very small, this is essentially a number times x to the r1. So that's very similar to that. And the next term would be, you can say it's a correction to the original solution. All right, let's see how it works. Two x y double prime, 2x squared y double prime minus xy plus, if we just say y, and this is Euler equation, right? Let's make it a little bit different. So this is not Euler equation. But when x is very small, this is essentially 1. So it's like an Euler equation. Or if you really go through the procedure, you can see q equals this, p equals that, then you times x, then this will give you negative 1/2, and if you go through this limit, x plus 1 over 2x squared times x squared, then this will convert to 1/2, like that, right? But the easier way is to write down your limit equation just by observing what is the dominant term. Here, 1 is the dominant term. So you can just write down that. Alright? So usually we write down the limit term by just observing the PQR and see what is the dominant term. Okay. Alright, let's solve this equation. This will give you 2r minus 1 minus r plus 1, right? And that equals 2r squared minus 3r plus 1, and that equals 2r minus 1r minus 1. And that equals 0 will give you R1 equals 1, R2 equals 1/2. Here we follow the convention that R1 is always chosen to be the larger one. If they're the same, then it doesn't matter. If there are two different real numbers, then we choose R1 to be the larger one. We don't consider the complex number case here. So we will assume our two solutions are two real numbers. Because, otherwise this will be a complex power that's hard to understand. So then this function, because it will appear again, let's give it a name. Let me call it capital F of R. And this R can take different values. For example, what is F1? Well, you plug in R equals 1, you will see it's 0. And F of 1/2, that's also 0, right? And F of any other number wouldn't be 0, right? So we just call this function F of R. Now let's try our test solution. It should be x to the r and an x to the n. Alright, that's the solution for the original function. And I didn't write on R1 or R2 here because it's easier to call it R and plug in the value of R1 or R2 in the end. And otherwise you have to do it twice. So we just keep the original, keep this generic form R, right? And but we know that R is either 1 or 1/2. Okay. So let's see, how do we handle the equation? We need to take a derivative, right? Well, if you do it directly, it looks like the product rule, but it's not that hard. It's actually easier than that. If you multiply R inside, you see it's not really a product rule. It's just a different power now, n plus R instead of n. So if you take a derivative, you will see it's an n plus r x to the n plus r minus 1, right? And this starting point is always 0 because n plus r is not going to disappear. And the y double prime would be an n plus r, n plus r minus 1 x to the n plus r minus 2. Okay, so you always have this plus r, right? Now let's plug into our equation. Our equation is here. 2x squared x, I missed prime here. 2x squared x and x plus 1. So we have 2x squared y double prime minus xy prime plus x plus 1 times y. But if you remember, we need to split because this term will have a different shift than that. So we split them. So the first one, 2 times x squared times y double prime. You see this? If you plus 2, it's cancelled. So you get an n plus r minus 1 x to the n plus r. Great, no shift is needed. Then the next one is an n plus r x to the n plus r. Remember there's minus 1, and now you have this plus 1, so it's cancelled again. Right, no shift is needed. And xy would have an x to the n plus r times x, right? We have that. Well, you need to do something to that because this is plus 1, right? So how do you do the shift? You replace n by n minus 1. So this is gone. And now n equals 1 to infinity because n minus 1 equals 0. Okay. And the last term, this is plus, The last term is just the original. an x to the n plus r. Okay, so there are 4 terms that add up to together, that add up to 0, and you can see 3 of them start from 0, and 1 of them starts from 1, right? So we can say if you add them up, you can just add up all of them starting from 1 with a special thing start from only for n equals 0. So summation n equals 1 to infinity. You have term 1, term 2, and let's add them together because they're all about an. You have an times 2 n plus r minus 1 minus n plus r plus 1, right? That take care of term 1, term 2, term 3. Then the last term is this, plus an minus 1. Right, and there's a special term that does not involve, not equal yet. A special term that only has this guy with no second term because there's no a negative and a negative 1. So a 0, then have this is n equals 0, and that equals 0. Oh, sorry, you have x to the r, because, when n equals 0, this is 0, so that's n plus x to the r. Okay, so this is a power series except there's x to the r, but it's equal to 0, so we just cross out all of that. So now you see a power series. This is a constant term, and then n equals 1, you get x, n equals 2, you get x squared, etc. So this becomes power series. And when will it be 0? If all of the coefficients are 0. So this equals 0 and that equals 0. Right? So let me write down more clearly. A0 to r minus 1 minus r plus 1 equals 0. And then you have the next term, an to n plus r minus 1 minus n plus r plus 1, right? Plus an plus 1 equals 0. Okay, this looks very complicated, but do you remember this term? 2r times r minus 1 minus r plus 1. That's exactly our f of r. See here? So, what do we see? This is this term here. The first term, the first term is just a, what's going on? The first term, why is it not writing? The first term is, sorry for that. The first term, you can write out this as a naught, a0 times f of r equals 0. And you can see this, and this is n plus r. And then you can, second term, you can write out an times f n plus r, right? You see here, compare the two equations. You can see all of the r is replaced by n plus r. So this simply says this. Oh, plus 1. Sorry. Is it plus 1? No, it's minus 1. Sorry. It's minus 1. Right? It's minus 1. So, well, it still looks confusing. But don't forget that r is either r1 or r2. Right? And in this case, it's 1 or 1/2. And now let's see, what is f of 1? Well, you see, f of 1 equals 0. F of 1/2 is also 0. So that equals 0. F of 1/2 is also equal to 0. So you can say this equation tells us that no matter whether r equals 1 or 1/2, you will get that's 0. So what is a0? A0 is arbitrary, right? Because a0 times 0 equals 0 does not tell you anything about a0. On the other hand, if this term will never be 0 again. Let's just take a look at the case that r equals 1. Okay, a0 is arbitrary. Then for this one, you can see an equals -1 over f of n plus r an minus 1, right? And what is f of n plus, what is fr? Fr equals here 2r r minus 1 minus r plus 1, 2r r minus 1 plus, minus r plus 1, right? And that means it's 2r squared minus 3r plus 1, and that is r minus 1, 2r minus 1. Well, we did that before, but now it's going to be applied to a more general argument. You replace r by n plus r. So you have n plus r minus 1 and 2 times n plus r minus 1, an minus 1. Alright, then we can plug in r equals 1. Okay, then you will see an equals -1. If r equals 1, this is just n, and this is the 2n plus 1, 2n plus 2 minus 1, right? 2n plus 1, an minus 1. So you can plug in the values. N equals 1, you get 1 times 3, then a2 equals -1 over n equals 2, so it's 2 times 5, which is 10, a1, and that's 1 over 30, a0. And you can see the denominator will never be 0, so you can get all the a's. So that means we can write down our first solution. y1 equals sum of a and x and, but don't forget there's x to the r in front. Okay, so, and in this case it's r1, so it's x because r equals 1. Then let me write on them just one by one. The first one is a0, then a1x, a2x squared, right? Then you can factor out a0. Then we have 1, and then a1 over a0 equals -1/3. And a2 equals a0 times 1/30, etc. Right? So that's your y1. y1 would be a power series times x. Alright, let's see what is our y2. y2 equals x to the r2, which is 1/2 times a new series. Okay, we still call it a, but that's all different. Okay, what's a0? It's arbitrary, right? What's a1? Well, we have to use this relation again. It's this one. Okay, not not this one, because you know we have different r now. Now r equals 1/2. Right? So let's see what do we have. Let me write down here. You have n plus 1/2, then minus 1, so you got n minus 1/2 in the denominator. And then you have 2n plus 1, then minus 1, so it's just 2n. Right? And you can reorganize them as n times 2n minus 1. Right? So that's your new denominator. It's not n times 2n plus 1, it's 2n times 2n minus 1. Right? That's the difference. So an equals negative 1 over n times 2n minus 1, an minus 1. Alright, let's see what is a1. You plug in n equals 1, you get negative 1 over, this is 1 times 1, so it's just 1. So negative a0. And plug in n equals 2, then 2 times, this is 3, so it's negative 1, 6. a1, so it's a negative 1, sorry, positive 1, 6. a0, and etc. And you can see denominator will always be positive. So we have your second solution. y2 equals, this time you have x to the 1/2, right? Don't forget that. Then times factor a0, and 1 minus x plus 1/6 x squared. That's your second solution. Alright, so if you want to put them together, you can write down y equals c1 y1 plus c2 y2. Well, you can see this c1 and c2 were not in your solution automatically, like last time, like for the ordinary points. But that's because we have this a0 here and a0 there. Although they are both a0, but they are totally independent. So still, you can say this is your c1, that's your c2. Okay? Or you can say, I don't want to call them part of the solution. I can say this is just 1. So that's your y2, and that's your y1. You know, they're equivalent. So just get your solutions and combine them like that. All right. So let's just write down the standard form. So c1, and what is x1? y1. y1 is 1 minus, let's see, what is it? 3 and 1/3. Plus c2 times x to the 1/2. 1 minus x plus. Okay, that's your final solution. You have two linearly independent solutions. One is like x, one is like x square root. Alright, that's what we do for a regular singular point. And although this is kind of lengthy, but every such problem would be similar. You always have this f of r appear somewhere in your recurrency relation. Okay. But there is one problem with this approach. When you have this recurrency relation, like here, like this, if we plug in r equals r1, then this denominator will not be 0 if n equals 1, because you know this will be r1 plus 1, right? That's not a root. And okay, by the way, when I say r1, I mean r1 is greater than or equal to r2, right? Then when you plug in r1, this number will take on value r1 plus 1, r1 plus 2, etc. And these values are not the root of f. because the root of f is only r1 or r2. But r1 plus 1, r1 plus 2, etc., well, they will never be r1 again, and they will never be r2 because it's larger than that. So you can always get a solution for y1. Y1 means corresponding to r1. But if you plug in r2, you will have a problem. You will have r2 plus 1, r2 plus 2 in your denominator, in this term. And if r1 and r2 are off by an integer, then at some point, for example, r2 plus 2 may happen to be r1, then you will have n plus r2 will be a root of f. So you have a 0 in the denominator, right? Then you have a problem. And I can show you one example that we run into such a problem. Okay, let's see example 2. It's called a Bessel equation. And so xy double prime plus y prime plus xy equals 0. Is 0 a regular singular point? Well, we can actually do this. We want to mimic the Euler equation, so we multiply it by x. Okay, so this is x squared, this is 1 times x, and what is this? Well, this, when x is very small, this is like 0, right? So we can just say, hey, we got our equation. It's just this. Plus 1 times xy double y prime plus 0 times y. Right? Because you take the limit, you will see this just becomes 0. So I'm just taking a shortcut here. Okay, if you want to be rigorous, you still need to take that PQ and RP ratio. Okay, but now I just find out this limit equation directly. Okay, so this is the Euler equation. Now let's see what's our root. So you have r, x. Then you will have r times r minus 1 plus r, right? And plus 0 equals 0. And that says r squared equals 0. Well, that will give you r equals 0. If you want, you can say they are both 0. Well, what does that mean? It means you can have y1 equals x to the r1 an x to the n. And unfortunately, r2 would be, y2 would have the same form. Well, that's a little bit different from what I tried to show, but it's similar. It means when you have the r1, r2 are off by an integer, you will run into problem when you use this technique. Although y1 will always work, but y2, in this case, you don't even have a form for y2. And there's some technique to find out y2. The y2, if you want, it can be written in this form. In this case, it's still same, but anyway, we write on that form. We run that, right? But it's not going to work because r1 equals r2. Then you have to do a thing that let's call it c times y1 times log x to make it work. But you have to determine this b, this a, and this c from your an, or maybe we just call this bn if you want. So this b and c will be determined on that an, and that's quite difficult. So we will not do this in this course. We will just say we are happy with just y1, and we will ignore y2. We just know that y2 can be obtained using this extra term. Alternatively, you can say, once we find out y1, we can find out y2 using the Wronskian, right? Well, that's still true, but it's not easy because the Wronskian would be a Wronskian will be a closed form function, or maybe an integral, but it's certainly not in the power series form. So you have to change the power series form, then integrate. Okay, then it's then it's not going to work because then it's not going to work because it's not going to work because the power series will be very complicated. So we will not do it in this class. We will just satisfied with just y1. Okay, so let's try to find out y1. Oh, let me say it again. So if r1 and r2 are the difference, let's say r1 minus r2 is not 0, 1, 2, 3, etc., then you can find out y1 and y2. And if r1 minus r2 equals 0, 1, 2, 3, etc., then we only find out y1. Okay, because we have to use a different technique to find out y2. All right, so let's see what is our y1. So okay, in this case, actually, we only need to find out one solution, right? So we can just plug in r1 directly, and you can see this is we don't really need it because r1 equals 0. So this is just the power series solution. So let's plug in the power series solution directly into our not this one, to the Bessel function. Okay, see, let's see what we get. X. Okay, how about we plug into this one? If you plug into this one, then you don't need to shift for the first one and second one. You only need to shift for the last one, right? So x squared x and x squared again. So x squared double y double prime, it's n equals 0 to infinity, a n minus 1 x to the n x y double x prime, sorry, that's a n x to the n, and the last term is x squared y, and that term you need a shift. And let's see how do you shift. You have to replace it by n minus 2, right? Then it's n equals 2 to infinity. Right? Okay, now let's add them up. If you add them up, you will see you have this plus that, and then this, right? So, and also this start from 2. So you will have sum start from 2, you have a(n). If you add up this with that, you get n squared minus n plus n, so it's just n squared. And by the way, this is just f of n, right? You know, because f of n is just n r squared. If you remember that, you know, this is just r squared, right? So this is f of r. So this is f of n. Then you have plus a(n minus 2 x to the n, and you have 2 extra term for x and a constant. For these two, you have a1 times 1 and a0 times 0, because you don't have that term. Alright, so it means all of the coefficients must be 0. So you have this equals 0, that equals 0, this equals 0. A0 times 0 equals 0 means A0 is arbitrary. And A1, on the other hand, times 1 equals 0 means A1 equals 0. Then you have the next term is a recurrence relation. Okay, here. An equals negative an minus 2 over n squared. And n is at least 2. So you will have A2 equals negative 1/4 A0 and A3 equals negative 1/9 A1, but that's already 0, so still 0. And A4 equals negative 1/16 times A2, and that equals 1/64 A0. And then you can see A5 is also 0, etc. Right, so you will see you only have even power terms. So your y would be A0 times 1, and then this term, you only have even power, and then this term. Okay, so that's your solution. And actually that's just y1. And how about y2? Well, as I said, because you cannot find y2 using the same technique, so we will just give up. It turned out that y2 would involve that y1 times log x. Okay. All right, that's for the Bessel function. All right, let's see one more example, then we will be done. This one would be 2xy double prime plus y prime plus xy equals 0. Okay, so let's find out the Euler equation. Well, once again, let me just times it by x. So you can see this top, this is like Euler part, this takes limit equals 0. So actually we can write down the limit equation just by doing this simple limit directly. Okay, so that's in a shortcut. Okay, this is the Euler equation and the limit equation, right? So we can just solve for this x to the r, and then 2r r minus 1 plus r equals 0, right? Okay, so we have 2r squared minus 2r then plus r, so this equals 0. So you have r and then 2r minus 1. Okay, then this will be called f of r. And 2r minus 1, yeah, okay. So let me plug in this, sorry, not plug in, I mean, then r1 equals the larger solution, which is 1/2, and r2 would be the smaller one, which is 0. So you have y1 corresponds to r1, y2 corresponds to r2. Okay, so let me just do it fast. So y can be assumed to be x to the r times a power series and then r eventually would be 1/2 or 0. Okay, but we're plugging later. Okay, so let me just do it fast. Y double x squared y double prime equals a n x to the n plus r. I have n plus r minus 1. And then xy prime, we should be quite familiar with this now. And the last term is x square y, and you have this n plus r, but you have plus 2, and do that. Then you do the shift, a n x to the n plus r, and this is minus 2, and this is from 2 to infinity. Okay, then add them up, and times this by 2, then add them up, right? So you get 0 equals n equals, see this is 2, from 2 to infinity, and add up this term and that term. So you have a n and the 2n plus r, n plus r minus 1 plus n plus r, right, plus a n minus 2 x to the n plus r, and then you have 2 extra term, right, x to the r plus 1 and x to the r, and that's for n equals 1 and 2, sorry, 1 and 0, because you don't have the second term. Okay, a1, and if you recognize this is just our f of n plus r, so this is f of r plus 1, and this is f of r. And because eventually we were plugging our r into f of r, so this will be 0, right? Because r is a root of f, so you have a0 is arbitrary, and because r equals 1 or 1/2, sorry, 1/2 or 0 implies r plus 1 equals 3/2 or 1, and neither is a root of f, so that's 0. Sorry, that's not 0. So which implies a1 equals 0, right? If this is not 0, then that is 0. So a1 is 0, then this will give you a relation between a2 and a0 and a4 and a2, etc. So you get 2 solutions, one for r1, one for r2. Okay, I just leave this to you to finish up. So eventually you will have y equals c1 times y1 would be x to the 1/2 times 1 plus something x squared, x to the 4th, something like that. Okay, and then the second one would be x to the 0, which is nothing, just nothing. You get a 1 plus something times x squared plus something times x to the 4th. Alright, so I leave this to yourself. Okay, let me do just one more example. Okay, sorry for that. Well, maybe that's it. Okay, we have done enough example. And I just want to tell you that I didn't show an example that a1 r1 minus r2 is integer, but as I explained earlier, if that happens, then you will have this f of n plus r happen to be 0 for a positive n, then you will run into trouble because you cannot determine an anymore. So that means our problem, our solution wouldn't work, and then we will simply just ignore that. Okay, and I think that's it for this section, and we will do the review next time and have exam after that.